Today we get to start picking up on some material that we started way back at the beginning of our cardiovascular system with respect to white blood cell production, white blood cell function, and even as we move into this immune topic a little bit more, a continuation of our discussion that we started with blood typing and antibody-antigen interactions. Today we're going to be sticking with purely innate immune system, and in other words, non-specific, non-adaptive immune system. We're going to look at frontline defenses, physical and chemical barriers that prevent infective agents from getting into the body, as well as some internal, non-specific secondary lines. And we say innate immune defenses. We're referring to things that aren't adaptive. We're not talking about immunity in the sense of the word that most people are going to throw that term around. I record this lecture in the time of COVID, and of course people are talking about an immune response that lasts, so once you get it, you're inoculated by vaccine, and therefore you can't catch it a second time. That's an adaptive defense. You catch something once, your body recognizes it, identifies it, it fights it off, and then from that point forward, you've got a standing guard, so to speak, in case that particular virus were to reinfect again. You can respond that much more quickly. Your innate defenses are not adaptable in that sense. They are the agents that you have present that is going to be the first to respond to any infective agent. They're not going to be specific to any one particular agent. These are going to include our surface barriers. If something is going to infect the body, it has to cross some barrier to get into the body. Skin, mucosal linings of the GI tract, lungs, whatever the case may be. Once it gets in there, we also have a system of internal defenses that are innate. But again, nothing that's going to be adaptive for today. When we look at the skin's going to be that most commonly thought of frontline barrier. Of course, we got that nice watertight barrier made up by the keratinized squamous cells, preventing things from entering, basically keeping the outside out and the inside in with respect to the body. We produce a sebum from the exocrine glands of the skin that has an antibacterial nature to it, bactericidal. So now what we see is, in addition to the acidic nature of the skin, pH of the skin is somewhere between 3 and 5, depending on the individual. The bactericidal, preventing bacterial growth, the acidic level, putting that bacteria in an environment that's outside its optimal environment for growth. Now what you've done is you've slowed down that invader. It's going to decrease the dose effect that invader happened to have once it got onto the skin. It's going to slow it down. It's going to put it in an environment enough that if we can keep it slowed down out there, it can die before it ever winds up getting into the body. Now, as we work our way through some of these different physical barriers, you will see that the nature of them slightly changes, but the overall theme is going to be the same. So if we move down the GI tract now, obviously in the stomach, significantly more acidic than what we saw on the outside of the skin. Now we're looking at a pH well below 3.5, typically somewhere between 1.5 and 3.5, an extremely acidic environment. We discussed that to a certain extent when we did enzymes. And we talked about salivary enzymes, that once you swallow that bolus of food and it winds up in the stomach, the acidic nature of the stomach renders any swallowed enzymes ineffective. Well, we get the benefit of that here by having an extremely acidic environment, so it's going to kill any foreign invaders that we happen to swallow. I shouldn't say any, but reduces the number that are going to be viable enough to infect in that manner. We see other bodily fluids, like the saliva and the lacrimal fluid. Now, in this case, we're going to see fluids that have these enzymes that can catalyze and destruct cell walls. Again, we think about the saliva as producing enzymes for digestion. But just what we mentioned here a little bit ago, they only really stay active while you're chewing up that food. As soon as you swallow, any salivary enzymes for digestion are rendered ineffective. But what they can do is remain available for attacking bacterial cell walls while they're in the mouth. So again, it jumps in early on fighting those foreign invaders. In the lacrimal fluid, we see an antibacterial agent, keeping the eye moist, but also taking what would have been a nice moist barrier for maybe an infective mode of transmission and giving it a chemical agent that makes that less likely. We move down the respiratory tract, and we see now not only do we have a mucosal lining that will trap bacteria, but we also have modified columnar cells. We have cilia that'll stick out into that mucosal lining. Anything that gets inhaled, that's particulate matter, gets lodged in the mucus, we can use the cilia to work it back up out of that respiratory tree. And of course, the last ones that we have to look at are going to be the mucosal linings of the vagina and the urinary tract. Again, we're looking at the most vulnerable ways that an infective agent can cross the physical barrier. Skin, respiratory, digestive, urinary, reproductive, and the moist barriers that would typically be associated with the nasal cavity and the eyes. Once we manage to get something inside and it gets a foothold, we want to have a number of different agents on guard, ready to capture and destroy whatever will have gotten past that frontline barrier. The first we have to look at, and some of these names are going to sound familiar because they come from our blood topics, but we have our phagocytes, the macrophages, the neutrophils. Now, back when we did blood, we just wanted you to know the basic function of those cells at that time. Here's where we're going to be requiring you to know just a little bit more about them. So please go back and reference those particular sets of notes for a little bit more in-depth material about the blood cells. But we're looking at phagocytes. Remember, those are going to be the cells that have these rather flexible membranes. They're going to recognize a bacteria. They're going to engulf it. Once engulfed, we see vesicles inside those white blood cells filled with enzymes. They merge with what was engulfed, and they break it down and destroy it. Natural killer cells are one we didn't really talk about back when we did blood. And let's face it, probably the catchiest name of any cell we'll wind up talking about. Now, natural killer cells are going to be still part of the innate immune system. They're non-specific. Generally, we rely on some degree of proteinous marker to be available on the cell wall of an infected cell. This is one of the mechanisms that helps our normal immune system from attacking healthy cells. When a cell becomes infected, it can produce any number of chemicals attracting attacking agents towards it, or it can present what's called a major histocompatibility complex. This is a protein that will be presented on the surface of an infected cell and can be recognized by other immune system agents. In the case of natural killer cells, they're able to attack these infected cells, these bacteria, without this early recognition. They don't rely on the secretion of these secreted chemicals, these presentation of these cell wall proteins. They're unique in that regard in that they are natural killer cells. They don't require that same activation. Now, these type of cells are going to be rather important because of timing. And really, that's what these innate immune agents are going to wind up giving us. Quick response, especially to something you have not been infected with prior. The natural killer cells are rather useful because, let's face it, they're going to be attacking cells that other white blood cells don't have the capability of attacking. Not only do not have the capability of attacking, these other white blood cells don't have the capability of recognizing that it's a problem. The natural killer cells have a way of sensing these stress cells, either that don't produce these proteinase markers on the cell wall or haven't produced them yet. So it's a jump start on attacking that foreign invader. We have eosinophils. Remember, these are the white blood cells that had those nice red granules. Now, whenever we talked about granulocytes, it's kind of worth noting that those granulocytes are vesicles inside the cell that store any number of chemicals. So when an eosinophil approaches a foreign invader or an infected cell, we can undergo this degranulation process. Whatever's in the granules inside the cell now gets dumped outside the cell in the vicinity of that foreign invader. Enzymes, peroxidases, major basic proteins, any of these that can interact with that foreign invader, break it down, and destroy it. Now, these do require a certain degree of recognition using the IgE antibodies and the Fc receptors that happen to be found on the cells. They recognize it, and that means they dump their contents of the vesicles, their granulation, in the vicinity, particularly for parasites, and we destroy the parasite in that manner. Basophils, kind of similar. Remember, basophils are also a granulocyte. In a basophil's granules, we're going to have histamine. Histamine is going to cause vasodilation. Histamine is going to increase the permeability to capillary walls for white blood cells. So we can get white blood cells leave the blood, pass through the capillaries, and make their way out into the tissues, maybe where the infection happens to be. We'll also see heparin secreted. Heparin is going to be an anticoagulant. And any number of proteolytic enzymes that may, through degranulation, again, break down the cell walls of foreign invaders. When we look at the inflammatory process, and some of these white blood cell actions are going to be involved with the inflammatory process, we really see 5 hallmark signs, 5 cardinal signs. We have pain, probably the most well-known sign of inflammation. Although, of course, you can have pain without inflammation as well. In the times of injury or infection, you can have heat produced. The skin over the area may get warm with that increased blood supply. The increased blood supply also may give a redness to the skin. As we see an increased permeability of the capillary walls, remember from the basophils, we may see fluid leave the cardiovascular system and flow out into the interstitial spaces, giving us swelling. And then for any of those reasons, really, we could wind up with loss of function, depending on which distinct tissues happen to be involved. We're all familiar with loss of function due to pain. Loss of function could also be secondary to extreme swelling. Or if there's injury to nerve, you may wind up having nerve damage as part of that inflammatory process, affecting whatever happens to be on the other end of that nerve. Now, when we talk about increasing permeability to a capillary wall, we have to look at in the context of chemical signaling. Chemical signaling is going to be rather important to the overall function of the immune system. if we are going to be responding to an infection, especially early on with this innate immune system, we're often going to be looking at quick responses in a localized area. So we want these infective agents that we're producing and that are in the body to migrate to where the infection happens to be. We are going to use a general method called positive chemotaxis. It's basically the migration of an agent in the direction of increasing chemical concentration. So in the capillary wall, we see the actions of the basophils increase the permeability for white blood cells. We get white blood cells adhere to the wall of the capillary, margination, and through diapedesis cross that capillary wall and go out into the tissues where the infection happens to be, the area of entry. From there, we are going to see chemical markers secreted from that area, from the tissues in that area. And as these agents get closer to that region, the concentration of those chemicals go up. You may have heard about something similar if you're into watching things like the National Geographic specials and whatnot. You know, they say, spectacular facts about sharks, for example, and how they can sense one drop of blood in like a million. And what they're doing is they're honing in on their prey through positive chemotaxis. You have an injured animal in the water that's bleeding. From a mile off, it's detecting the ever so slight concentrations of that blood in the water. But as it gets closer, the concentration of that blood goes up and up and up. So it's honing in on its prey through this positive chemotaxis. Innate immune agents make their way to the site of infection by way of positive chemotaxis. We have any number of antimicrobial proteins that could be involved in our innate immune system. And the first one we look at is through a process called optimization. I'm sorry, not optimization, opsinization. Optimization is completely different. Opsinization. Please, if it's on a fill in the blank, don't get that one confused. Opsinization is part of the process of marking an invader for recognition. So we mentioned macrophages previously. Macrophages use this quite a bit. We have a phagocytic cell with a complementary receptor looking to detect foreign invaders. A complementary protein could bind to the bacteria in question. Now, here is our means of identification. Now, this kind of goes back a little bit to what we were talking about with our natural killer cells. They have the ability to detect an attack without this chemical marker or this other chemical mediator. Unfortunately, things like macrophages don't have that luxury. But through the process of opsonization, we do get that protein-protein binding ability. We bind to our complementary proteins, which is already bound to the bacteria, and then we can engulf the entire lot into the cell and break it down. We can take bacteria or other infected cells through the process of cytolysis, the splitting of a cell, using these non-specific membrane attack complexes. We have an infected cell, any pathogen membrane, that happens to have the antibodies that are adhered to it. These complementary proteins can now bond to the antibodies and embed their membrane attack proteins into the membrane of the pathogen. This membrane embedding protein forms a pore that disrupts the pathogen from being able to maintain its intracellular homeostasis. Remember how important the membrane was when we talked about it in A&P1. That membrane bilayer is fantastic at keeping what's outside out and what's inside in, and allowing us to control the internal and external cellular contents. We stick this large pore into the membrane of a pathogen, and it opens up a garage door, so to speak, to allow anything and everything to enter and leave the cell. Without being able to maintain its intracellular contents, that cell is going to split and die. Next up, we see chemical signaling in the way of interferons. Now, with COVID, again, being prevalent as I record this, in passing, you've probably heard quite a bit of these chemical markers, because this is one of the innate responses we have to a viral infection. Now, unfortunately, it kind of has to get to a point where we do have infected cells with that virus. But if we look at what's happening in the timeline of this diagram, virus enters the cell. Now, a virus can't sustain itself. It basically hijacks a cell and uses its infrastructure to replicate itself. So it'll hijack the cell. It'll take over the DNA sequence. It'll take over the replication cycles and start producing more copies of the virus that can then be ejected out to infect other cells. Well, once a cell becomes infected, it's aware of this. And one of its responses is it can't really save itself at that point, but it can produce these interferon molecules, which can be dumped outside the cell. And if they can reach the neighboring cells before the replicated virus does, it can trigger an early protective mechanism on behalf of the cell that hasn't been affected yet, so that now when a virus enters that second cell, it's got antiviral proteins ready and waiting to respond to that viral infection. Again, non-specific, non-adaptive, but a way of giving us a really early response, even if it's non-specific, not going to be as efficient as our adaptive immune agents are going to be when we talk about them. But early response that's quick to slow down any foreign invader from getting a foothold into the body. The development of fevers work in a similar way. Sometimes we think of a fever as, an unwanted symptom, right? But it is a normal part of the response. Once you detect a foreign invader has entered the body, particularly viral or bacterial, macrophages secrete pyrogens. Pyrogens make their way to the hypothalamus and change the temperature setting. It's going to excite cold sensing neurons in the hypothalamus. Your body thinks it's colder than it really is. It's tricked into thinking it's colder than it really is. And as a result, it raises body temperature. Now, that raised body temperature might be stressful on the body as a whole, but it's also extremely stressful on any microbe that happened to enter the body. And in this way, it slows down that progression of what just entered the body in an infective nature. Slows it down, prevents it from getting a foothold, and allows us to mount an aggressive attack. These pyrogens also trigger the liver and the spleen to take up things like iron and zinc, which many bacterial infective agents happen to need extensively. So not only is it going to turn up the heat on it to put it in an environment that's not optimal, it's going to take up the resources and try and starve it out at the same time. So again, mostly in a bacterial setting, but occasionally in a virus as well. See, these phagocytic cells secrete these pyrogenic agents, changing the setting in the hypothalamus, and basically changing the body into an environment that's less conducive for the foreign invader. So we're really into a realm of a lot of memorization here for this. We'll have to get into more understanding when it comes to our adaptive system. But compartmentalize this material as best you can. Surface frontline defenses. Understand that we've got things like particular pHs that are non-optimal for bacterial growth. We've got bactericidal chemicals that happen to be in things like skin, the sebum of the skin. We got enzymes that may be in the saliva and the tears production. All in a way of anything that hits one of those surfaces, it's already in an environment where it's tougher for it to survive. If it does make its way into the body, we've got these chemical and cellular agents at the ready, still non-specific, that are ready to spring into action. We have our phagocytes. We have our basophils. We have our eosinophils secreting chemicals. And we've got our chemical agents like interferons ready to signal to non-infected cells that something may be coming their way. So again, for the details of the white blood cells, please head back to the chapter in the notes on blood. Get that detail there. And if you have any questions, please let me know.